All right, so types of chemical reactions. We're going to cover three broad classes of reactions that are going to happen in solution. Precipitation reactions, acid-base reactions, and oxidation or redox reactions. This last one we're going to cover very briefly. I'll want you to know how to identify them, figure out which one's being oxidized, which one's being reduced. You will get into more detail when you start doing electrochem in the next class. Right? So let's look at our precipitation reactions. Right? This is some classic old school bench chemistry that if you've had chemistry in high school, you probably have already done. Right? So precipitation reaction is one in which you mix two solutions and it results in the formation of an insoluble substance which separates from the solution. And that solid is called a precipitate, and sometimes you'll see PPT as an abbreviation for that. So our precipitate, identification of the precipitate requires knowledge of the chemical composition of the solutions, right? So you can't just take two random things and say, I formed a precipitate. You got to know what your starting materials are to figure out whether or not it's going to make a precipitate. And there are some rules for that, right? So here's a great picture of that. This looks like it is a solution of, this is probably lead nitrate, PbNO3, 2. This looks like it's either sodium or potassium iodide, and it forms this very characteristic lead iodide solid precipitate. Okay. So let's take a mixture of solutions. So we got potassium chromate and barium nitrate. Right? Potassium chromate is going to be in solution, as will the barium nitrate be. Recognize that when a solid dissolves in water, those ions are going to separate. So our potassium chromate is going to be dissolved into K plus and CrO4 2 minus ions. And we'll actually have two of those. And our barium is going to be separated into barium 2 plus and nitrate ions. When we mix these things together, we're going to start out with the following ions: potassium, chromate, barium, and nitrate. The compound that is formed has to have a net zero charge, so both anions and cations are going to be present in the product. So one of the things that I always found that was really confusing was like, but what's going to happen with the other thing, right? So you got all these things floating in solution. Let's take a look at the possible interactions that we can have, right? So we can have a potassium interacting with a potassium, right? So anything that's going to interact with itself, right, is just not going to happen, right? So the potassium interacting with itself, the chromium, the barium, the nitrate, right? We look at this, we're like, here's a plus charge, not going to happen, right? If I look at the nitrate, right, it's got a minus charge on it, and it's going to see another nitrate, and they're going to be like, no, right? So really, you want to look at these ion pairs. So if we call this guy A, B, and C and D, our possibilities are going to be that A can interact with B, C, or D. Right? Well, we already know that A and B are going to split up. Right? So A and B aren't going to react. If I take A and C, well, A is a +1, and this is a plus charge. So my potassium and my bromine, Br2 plus, right? They're not going to form a reaction. Nothing's going to happen. Right? So my like charges won't happen. So my chromate, CrO4 2 minus, right, plus the nitrate, right? Not going to happen. Right? So the only real possibilities we can get is what's called a double displacement reaction, where you're going to have A and AB plus CD, and the only possible things we can get are going to be the reaction between A and maybe D. So we're going to form A, D, or CB as potential products. These may or may not be soluble. What we're going to see is some of these things are going to be soluble, some of them won't be. So if you can memorize this pattern, AB plus CD gives me products of AD and CB, where they've kind of swapped themselves around. They swapped partners, right? That's going to be the only way we can have these two interactions. This may be a precipitate. This may be a precipitate. Neither might be a precipitate. They both might be a precipitate. We'll have to look at the rules. All right, so we got a couple of different combinations: potassium chromate, potassium nitrate, barium chromate, or barium nitrate. Right? We already said barium nitrate, not going to happen. Right? We already said potassium chromate's not going to happen, otherwise it wouldn't be coming in solution. So the only possible ones we've got are the potassium nitrate and the barium chromate. The potassium chromate and the barium nitrate are the reactants. They're not going to react with each. They're not going to form themselves again. The substance that is formed is going to be yellow in color. Potassium nitrate is a white color, and barium chromate is a yellow color. So the solid that is formed is almost certainly going to be barium chromate. If the potassium nitrate is mixed in the same quantity of water as the mixed solution, it will not form a solid. So if I take regular old potassium nitrate, dissolve it, I'm not going to form a solid. Right? It's a very soluble solid. So therefore, my reaction is I've got potassium chromate and barium nitrate forming barium chromate and 2 potassium nitrates, but these guys are going to stay in aqueous solution, so we'll keep the AQ. These guys started out as aqueous solutions, and it is our barium chromate that forms our solid precipitate. Okay? So how do we know which ones are going to form which ones? Right? 2 ways to know. There are some rules, and then there is a table. Right? There's a table you can look stuff up on. You're like, okay, what about potassium and nitrate? Does that follow a thing? What about barium and chromate? Is that soluble or insoluble? You look up on your solubility table. The other way is to use some of these rules, right? So there are very few things I'm going to ask you explicitly to memorize. This is one of these things that I'm going to ask you to memorize. We're going to go over the rules, but I'm going to ask you to memorize 3 of them. Right? So if a compound is soluble, if it contains one of the following cations, right? A group 1 cation, lithium, sodium, potassium, cesium, francium, or ammonium. Right? So if you're in column 1, you're one of these guys with a +1 charge cation, you will be soluble. Right? But it's only going to be these +1 cations that we can go for that are in group 1 and ammonia. So anything with lithium in it will be soluble. Anything with sodium in it will be soluble. Right? All sodium solubles are going to be, all sodium solutions will be soluble in aqueous solution. So memorize this one. And that's one thing to memorize. Any compound is probably soluble if it contains any of the following. Right? If it's a halide, so all chlorides are soluble except silver, mercury, and lead. All bromides are soluble except silver, mercury, and lead. I talked about that picture where we had the very yellow, distinct yellow color for the lead iodide, right? Lead iodide is one of the exceptions. So memorize these guys and their exceptions. Right? All nitrates are soluble. Right? That's thing number 3 to memorize. So if I've got lead nitrate, it's soluble. If I've got sodium nitrate, it's definitely soluble because nitrate and sodium are both going to be soluble. If I've got anything with a nitrate on it, that's why we see so many of these nitrate compounds and why nitrate is going to be such a familiar friend to us. That's because all of those nitrate compounds are soluble. Now, nitrite, NO2, no, not all of those are soluble, but nitrates, all nitrates are soluble. Right, so those are our 3 things. Group 1 all group 1 cations are soluble. All halides are soluble except silver, mercury, and lead. All nitrates are soluble. If you memorize those 3, it's going to cover 80% of your precipitation reactions, and it will get you through stuff that much faster. Right? Pretty much all perchlorates, acetates are soluble. Most sulfates, except for barium, mercury, and lead, are going to be soluble. And there's a bunch of other rules, and then there's exceptions to rules. So really, in practice, you would look at that chart and go, okay, well, here is a chart of solubilities. What things are going to be soluble? Right, so here's one of those charts. There's lots of different versions of these charts out there, but let's say we have magnesium bromide, right? So here I've got magnesium. I'll look at my magnesium 2 plus, and I go over to where bromide is, and it's soluble, right? And all of our bromides are soluble except for silver and lead, and it doesn't have mercury up on this one, but mercury is not going to be soluble, right? So you could look it up on a chart, or you could memorize some of the rules. Right? How many of the rules are you going to memorize? 3. 3 shall be the number of rules that you shall memorize, and the number of rules that you shall memorize will be 3. Now, let's predict what will happen when aqueous solutions of sodium sulfate and lead nitrate are going to be mixed. Right? So the ions that are present are going to be sodium, sulfate, lead 2 plus, and nitrate. Right? They're going to do their little dance. They're going to do-si-do and switch partners, right? Because sodium and sulfate and lead and nitrate are not going to hook up with each other. So we're going to make sodium nitrate. And what's our rules for sodium compounds? Right? Sodium nitrate is going to be soluble. Why? Because sodium is one of our +1 cations in group 1. And all nitrates are soluble. So this guy, right? Nobody wants to dance with poor nitrate. Nitrate just stands alone. Now we got to consider the lead and the sulfate. So for that, I'll take it back one, look at my lead. Right, there's my SO4, and I'm looking for lead, Pb, insoluble. So our lead nitrate would be insoluble. It's not one of those ones we memorize, but if you see a precipitate, we know it cannot be coming from the sodium nitrate. So it's the lead sulfate that's going to form the precipitate. So when we write this balanced chemical equation out, we'll do Na2SO4, sodium sulfate AQ, lead nitrate AQ. They're going to dissolve, and we're going to form lead sulfate solid and sodium nitrate aqueous. So which of the following ions are going to form compounds with lead 2 plus that are going to be soluble in water? Okay. Well, this one, because they're not going to interact at all. Right? Sodium won't at all. Right? We just said lead sulfate will be insoluble. All nitrates are soluble. Right? Now, all chlorides are soluble, but not silver, mercury, or lead, so this guy's going to be insoluble. And then we got this sulfide, so we got to go back and look and see, well, looking up at our table, do we have sulfide on here? Yep. And do we have lead? It's going to be insoluble. Right, so our lead sulfide will be insoluble. Just like we have different ways of representing molecular formulas, like empirical, molecular, and structural, we have different ways of representing reactions that happen in aqueous solution. Specifically, there are 3 ways. What we've seen so far is what's called the molecular representation. That's going to show all our compounds represented by their formulas and balanced and showing their states, right, in parentheses, like AQ or solid. And if it says AQ, it's kind of up to the person who is reading it to figure out, well, is that going to dissociate into ions as an ionic compound, or is it just going to dissolve like sugar? So, you know, it's missing a little bit of information. Our total ionic equation, our TIE, shows all our strong electrolytes as ions and insoluble substances as compounds. So if it's NaCl AQ, right, it's going to break that up into Na plus explicitly and Cl minus. Right, and anything that's going to be a molecular compound like sugar or ethanol, C2H6O, right, we could put that as AQ, right, but that's not going to dissociate. And then net ionic is going to be similar to that, but it's only going to show the stuff that are going to show up as changing in our reaction. We're going to remove what we call spectator ions, right?